Okay, we are picking up where we left off last time in our notes. Before we get going, I just want to remind you to have your notes out in front of you so that you can record stuff as we go through this. I also want to remind you of what we talked about last time. So we spent a lot of time talking about waves, specifically because of the wave-particle duality that exists for electrons. We looked at the relationship between the speed of light as well as wavelength and frequency. Remember that wavelength is represented by lambda and frequency is represented by nu. This is in V, this is nu. This right here is an indirect relationship. That means that as our wavelength increases, our frequency must decrease. We also looked at energy. And remember that our frequency is related to our energy through Planck's constant. Planck's constant is represented by this H right here. And this is a direct relationship. So as our frequency increases, our energy increases as well. We also finished off by talking about the Bohr model. And remember, the Bohr model was important because it gave us the idea that there are discrete energy levels within the atom that the electron must exist in. And that's going to be what we talk about today a little bit. But there were some problems with the Bohr models. Of course, it only worked for hydrogen, which is kind of an issue because there's a bunch more elements on the periodic table. And remember that Bohr also didn't know much about this idea of quantum mechanics. So he represented the atom as a nucleus in the center with these circular orbits that the electrons traveled in. We now know that that's not true, and we'll get into that a little bit more today. Before we get going, I just wanted to start off with some completely unrelated photos of Barkin, my dog. I just thought it might brighten the mood a little bit here. So we'll start off with him looking really regal. There he is. That's not usually how he looks. He usually looks like this. He's a total dork. That is him in his cone because he managed to injure his ear. Anyway, so with Barkin aside, we will move on to what's actually going on today. So we are going to look at the wave nature of matter. And Louis de Broglie, I'm not exactly sure. He basically was actually able to take wavelength and relate it directly to matter. He believed that all matter should exhibit some wave-like properties. And the equation that he came up with is represented right here. So we have lambda, which is our wavelength, and that equals Planck's constant over the m here represents mass, and the v actually is not nu in this case. This is v as in velocity, as in meters per second. And so through this equation, we're able to do things like this electron micrograph over here. So basically, if we take Planck's constant and divide it by our mass times our velocity, we should get a wavelength, or the wavelength that applies to whatever matter we're talking about. So what I'd like you to do is to do a little bit of a calculation for yourself. So I want you to figure out what your wavelength would be if you were running at 100 meters per second. Imagine the stick figure guy right here is you. So the first thing you're going to need to do here, and you should be doing this calculation in your notes, there's a space for you to do that, is you need to take your mass, which is in pounds, and convert that into kilograms, okay? And then we're going to plug it into this formula right here and solve. So we're going to pause for a second. I want you to see what your actual wavelength is. Okay, so you should have done this calculation and you should have ended up with some wavelength. Your wavelength should be in meters. And what you should notice is that your wavelength is really, really, really small. And that's because you have a big mass, right? Mass is on the bottom here. So you're going to have a really small wavelength. When I did this calculation for myself, I came up with 1.2 times 10 to the negative 37 meters. So that's a very, very small number. What you can see is if we have something that's really small, then we're going to have, the wavelength is going to become much more important. So expanding on this and well, or related to this, is what Heisenberg came up with. So this is the Heisenberg uncertainty principle, which we did talk about a little bit in regular chemistry. And what Heisenberg showed was that you can't really know the momentum or velocity of an electron and its location at the same time. And we do have a special equation for this. You will not be really required to do this on the AP exam or test in here. But basically what this is showing us is that for a range of x values, that would be like our location, and a range of momentum values, if you multiply those together, it has to be bigger than this value right here, which means that if this range goes to 0, so if you know the location more precisely, then you have to have a bigger range for your momentum in order to be greater than or equal to this value over here. Similarly, if you know really precisely this, if your range that you're looking at for your momentum becomes really small, then this number right here has to become really big in order to compensate, and still be larger than this value over here. So this means that for electrons, we cannot determine their location and speed or momentum simultaneously. So Schrödinger developed a mathematical way to combine the wave and particle nature of matter into a single form, so that we could look at, for example, where or the regions where electrons might be in the atom, and this is called quantum mechanics. And if you look off to this image at the right, and I'm not sure if it appears very well in your notes, you might need to kind of fill it in. What he did was he was able to kind of look at what we now consider orbitals and or the places where electrons are likely to be in the atom by doing some pretty high level math. And what it would look like is you'd see kind of these speckles that represent where you're most likely to see electrons. So here, where you see some dense coloring, that's where you'd be most likely to see an electron in this orbital. Out here, where there's fewer dots, where it gets lighter, that's where it would be less likely. Okay, so Schrödinger had the wave equation is what you would solve, or you would use in order to describe where these different electrons are located. And we use the Greek symbol psi, this right here, it looks kind of like a triton, to describe where these electrons are. And the square of that gives us the electron density, or the probability of where an electron is likely to be at any given time. So in your notes, I'm not sure that the psi is that the definition of psi is really given there. So if you want to like circle that in your notes and write electron density next to it, so that when you come back to it and you see this this funky symbol, you'll know what it means. So again, here where you would see this density, that's where we would be most likely to see the electrons in the atom. Okay, and this is our orbital, for example. Different orbitals have different energies, and what we're going to do is we're going to describe those orbitals using a set of what are called quantum numbers. And we didn't do this in regular chemistry. This is another way to kind of show where electrons might be, and to describe, for example, how they're spinning, that sort of thing. So each orbital is a spatial distribution of electron density. And they're not just those circles in the Bohr model, right? They have these different kind of interesting shapes and stuff, which we'll get into a little bit later. So the quantum numbers that we need to go over here are, we're going to start with the principal quantum number. And I do want to warn you, your notes are not going to match up exactly with what's the words on the screen here. So you might need to kind of interpret as you're going along here, add some stuff in, that sort of thing. So we're going to start with the principal quantum number. It's represented by the letter n, this lowercase n right here. And what this does is it describes the energy level that the orbital's on. So all of the n values that you can have are going to be greater than 1. So for example, the 1 electron in hydrogen its principal quantum number is going to be 1 because it's in the first energy level. These values correspond to the Bohr model. So you can see that even though the Bohr model is not perfect, we're still kind of continuing to build off of some of those ideas. Okay. So again, this is the principal quantum number. It's n, and all n values have to be greater than 1. And this is kind of like, if you think about it, this is your energy level. The next quantum number that we have is the angular momentum quantum number. And it's represented by an L. So this is a lowercase l right here. And what this does is it tells you the shape of the orbital. So for example, it's spherical, like an s orbital, or it's dumbbell shaped, like a p orbital. The only values that we can have for L are from 0 to n minus 1. Okay, from 0 to n minus 1. So if we're looking at hydrogen and that one electron in hydrogen, right, its only n value it can have is 1. So that means that the L value, or the angular momentum of that, is going to be 0 because n minus 1 is 0. And so as you get more complicated, right, you can have larger sets of these quantum numbers. And so we're going to use some numbers here, but those numbers correspond to the letters that you've seen before that describe the different orbitals. So if we go one more slide here, you can see here, if we have the angular momentum value, that L, if it's 0, then we're looking at an s orbital. If it's 1, we're looking at a p orbital. If it's 2, we're looking at a d orbital. If your L value is 3, then we're looking at the f orbital. Okay, so you might want to, in your notes, the values are given there, but it doesn't say like that 0 is S necessarily and P is 1. You might want to jot that down, or above the SPD F orbital labels, put in these numerical values. And remember, angular momentum values, or the angular momentum number, L, it's telling us the shape of the orbital. So the next quantum number that we have is the magnetic quantum number, and it is designated as M sub L. So this little subscript right here is an L. And what this is telling us is the orientation of our orbitals. So remember that these orbitals exist in three-dimensional space. So they can be lying along the x-axis, the y-axis, or the z-axis. The n values are going to range from negative L to positive L. And what this ends up giving you is that you can have only one s orbital, only 3 p orbitals, 5 d orbitals, and 7 f orbitals. So you can remember from regular chemistry, or the way the periodic table is set up, that you've seen these numbers before, right? For example, if you look to the p block, right, each orbital can contain 2 electrons, and if you go across there, there's 6 total spaces. So that means that we can only have 3 p orbitals. Orbitals with the same value of n form an electron shell. So we're getting into some vocabulary here, and just some vocabulary that you need to know. And this table is in your notes. It's also directly from your textbook. And these words that are on top here are actually on the bottom of the table there. You might want to note, this is important because people frequently confuse this vocabulary. So if the orbitals have the same n value, the same principal quantum number, then they are in the same electron shell. But the different orbital types within that electron shell, those are called subshells. So in the third energy level, right, there's the 3s, the 3p, and the 3d. These are all subshells right here, but this is one shell. Okay, we have one other quantum number that we didn't really mention yet, and that's ms, which is the spin quantum numbers. And so what they discovered in the 1920s was that 2 electrons, even if they're in the same orbital, they don't have exactly the same energy. And what happens is this is because of the magnetic field that the electron that describes the electron. So you can think about this as them spinning in opposite directions, and we have a little image over here illustrating that. But the way we do it in terms of the quantum number is that we assign them an either positive 1/2 or negative 1/2 value. So what this means is that no two electrons are going to have the same set of quantum numbers. So if they're in the same orbital and the same energy level, they're going to be differentiated by this spin quantum number is either plus 1/2 or negative 1/2. Okay, so let's get into the specific types of orbitals that we have. The first one is the s orbital, and it's a spherical shape. And I think I included some images of it in your notes as well. Not super exciting. It looks just kind of like these circles here. And what it really looks like is more like this electron density model here, where there's all of these different probabilities of places that the electron could lie, but the largest probability is close to this shape right here. And so as we increase our principal quantum number, our n value, basically what's happening is the radius of the sphere is increasing. So if you're in the first energy level, you would be this smaller sphere. And then if you had electrons in the second one, they would be farther out here, the third one, etc. So they become kind of like these concentric spheres, which represent the different areas that the electron would likely be in. Okay. For these different orbitals, so you could also represent this as a graph. That's what's going on here. This is the probability of where an electron would lie. So on the x-axis we have the distance from the nucleus, and then we have how likely it is to be there. And what you'll see is in the 1s, right, they're all grouped around this distance. So here we have the 1s and then the 2s. And you'll notice that there's this dip right here in the middle where no electrons are likely to be. That's called a node. And you'll see that right here we're just looking at between different energy levels of the s orbital, but you'll see that in the p orbital and the d orbital, etc. You'll see that there are some places where electrons can't be, and we refer to those as nodes. It's a place where there's zero probability of finding an electron. And in this case, if we matched it up to the spherical image that we were looking at, you can see it's as you get to the outer edge of the 1s, right, then we have this place where there's no electrons that'll show up. One thing to remember is as you increase your value of n, you are more likely to find an electron farther from the nucleus, and that kind of makes sense, right? Because as your energy levels increase, you're getting farther and farther from the nucleus. One note to add in there too is this right here. So for an s orbital, the number of nodes is given by n minus 1. That's the principal quantum number minus 1. Okay, so that's how we calculate the nodes. That's something that you're going to need to fill in on your notes. Moving on to the p orbital. So we call this a dumbbell shape. And so you can see the electron density map here and how that maps to this dumbbell shape right here. So there are 3 different types of p orbitals. There's the px, py, and pz. These letters, these subscripts down here, represent the axis that the orbital would lie along. So this one would be on your x-axis, to be this one right here. This one would be on your y-axis, and this one would be on your z-axis. The L value for P is going to be 1. You might want to write that down. I'm not sure that is clearly in your notes. And basically what happens is that we have these 2 lobes that represent the parts of the dumbbell with the space in the center. That is the node for the p orbital. And no electrons are going to exist right there. Okay. Actually, I want to go back to the slide just because I think that there are some notes on there that aren't on this. So on your notes, I think that there's a place where it says the letters corresponding to allowed values of m sub L. So in there, you're supposed to fill in -1, 0, and 1. So it's just going back to going back to the m sub L, which is represented by that's the magnetic quantum number. It's just the options for p orbitals. Okay, so now let's move on to our d orbitals, which has my personal favorite orbital in it, which is this dumbbell with the donut around it. Just looks kind of silly. But most of them look more like these clovers right here, or a double dumbbell. And again, they can lie along different axes. And there are 5 different d orbitals that are possible. The L value for this is going to be 2. And any place where you can see where they connect. So here we would have a node in the center. Here we would have a node in the center. And then we have these different lobes where electrons can be located. Okay, so in your notes, you don't need to fill out all of this stuff here, just that there are 5 d orbitals. And in terms of F, there are 7 F orbitals. And the shapes get really, really complicated. I may have included some of these in your note sheet. You might want to write down, however, that the L for this would be 3. Remember, L is your angular momentum quantum number. Okay, and you won't really deal with the F orbitals too much, just because it gets so much more. It gets increasingly complicated as we get out here to the D and the F orbitals. Okay, I think this is where we're gonna stop. Thank you for watching, and I'll see you next time.